Hello all. Hi, I'm Alex Abrilla, and my project focuses on implementing these non-isometric flows on planar curves via reduced coordinates. And really this generalizes part of the work, at least, of Keenan Crane and some others when they were working with curvature reducing flows in, well, really mainly for surfaces in R3, but also for curves. And the way they did this is, let's say you have some curve, which is this, you have this parameterization in the plane, and then we can discretize it by taking a couple of points and linearly interpolating between them, kind of this piecewise thing. And then in the smooth setting, if we want to run a curvature shortening flow, really what we can do is we can say we have this energy functional, which we're going to call this the Willmore energy. And then we're going to go to minimize it. And we're going to say that the minimizer is, well, it's what's called an elastica, but really it has these nice smooth properties. So in order to replicate the discrete setting, we consider the discretization of the Willmore energy, which is this expression here. And once we have this, it kind of makes sense to run the flow in terms of these reduced coordinates, or really in terms of the lengths and curvatures of a planar curve, which completely describe it. And instead of like maybe the positions, or instead of thinking about it like some kind of point cloud. So this leads to the algorithm where, okay, given a curve, which is a discrete curve, which is represented as a set of points, we first translate it into this intrinsic setting, and then we calculate the gradient with respect to the lengths and curvatures. And there's some complications here because there's interplay between the lengths and curvatures. But then we have some conditions maybe that we're trying to preserve. So say, for example, that the curve is closed. Then we want to make sure that as we perform the flow, the curve stays closed. And this gives rise to some conditions which affect the gradient. So we compute the projections of the gradient onto these constraints, and then we subtract those off. The second step here. Third step. And then there's still some discretization error though, so we minimize that by solving a Poisson equation, and then we perform this forward Euler step where the curvatures and whatnot are updated with the gradient, and then the curve is reconstructed. Okay. So my contribution is considering these three different energies and how they perform in the non-isometric setting when lengths are not preserved. The work done by Keenan was under the assumption that lengths are preserved. And so we can kind of compare these in the small case, and they perform as we might expect. So let's say we start with this shape here. Then if we perform the Willmore flow, this energy, minimizing this energy on it, we see that all edge lengths actually are going to blow up because we can just minimize this by increasing the edge lengths without bound, and it'll go to 0, which maybe is not that interesting. But if we control the step rate, or the step size, then this leads to some nice looking smooth curves, because we see that kind of the curvature at each vertex gets very equally distributed because we're able to elongate shorter edge lengths, and that's nice. Whereas, okay, if we consider maybe this sum of curvature squared, which will not affect the edge lengths, we don't get that property. Okay. However, things start to get a lot more complicated as we increase the number of vertices. So if you look at this rabbit here, for example, poor rabbit's going to get deformed. We see when we run the Willmore flow and also the squared length flow, degeneracies start to occur, where if we update the edge length at too large a rate relative to the curvatures, then everything blows up and we lose stability, and the flow is no longer meaningful. So in order to perform those two flows, we need to take a much smaller step. And in addition, we need to introduce kind of this scaling parameter g, which updates the length parameters relative to the curvature parameters at some prescribed rate. We found that g equals 0.1 works kind of well when h is around this size. And this produces somewhat stable flows, although still somewhat lacking because, as you can kind of see here, these cusps develop. And the reason we think for that is because of some reconstruction procedure that we're going through. There is some good news, though, in the larger case, and that's that the squared curvature flow actually still performs very well, and that's because it's largely unaffected by the edges. You know, it's independent of the edges here, the edge lengths here. And because of that, we can take somewhat arbitrarily large step sizes. We found that h less than 0.5 tends to work pretty well for arbitrarily large inputs. And this leads to a pretty fast rate of convergence relative to the Willmore squared length flows. That's pretty good. If you'd like to try it, we have a demo here, so you can go and play around with it. Here's like Wilmore flow, integrating this flow. Because this is small, we can bump it up a bit and we say, oh, look, it blows up. Okay, it gets large. You can also switch the settings and whatnot, so have fun with that. And then in terms of future work, there's still a lot to be done, to be honest. We need to investigate the formation of these sharp cusps, and there are other types of energies we can investigate other than these Wilmore flow, like Wilmore energies and variants of that. And then there's also the question of like, okay, maybe we can go to 3 dimensions with these space curves and work on minimizing curvature there. And then there's also the question of non-isometric or maybe non-area preserving flows for surfaces. So there's a lot to generalize. And here's some references. Thanks for listening.